so you can see my slide.
Yes.
All right.
You can have the control of the screen.
Okay.
Let's go ahead. No worry. So I'll be back. I'll be back in like 3 minutes. So you can feel free to prefer to share the screen. If not, I can also share the poster. Either way, you can share.
I will be just sharing my screen like this.
That is great.
Okay.
I think we can gradually start. People might still join in. So let me also press the recording.
So should I go ahead or?
Welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar series. It is our great honor and pleasure to invite Professor Jung Hoon from SKKU University. I'm not exactly sure how to pronounce that, but maybe Professor Han can teach us. I think Professor Han is currently also visiting Harvard Condensed Matter Group, and he'll be speaking about several of his recent works. The topic is lattice gauge theory review of Toric's SQ and more. I'd like to remind the audience, if you find the appropriate time you want to interact, ask questions during the talk, please feel free. So let us directly welcome Professor Han.
So
thank you.
Yeah, so thank you very much, Juvin, Dr. Wang. It's a great pleasure to be speaking to the audience here. So, so this is based on some work that were published over the past year or so. And additionally, some recent preprints that we posted in the past 2 weeks or so. And because I have a very short collaborator list, let me actually start by acknowledging them. My student Jin-tae and my postdoc Yun-tak. I think both of them are here online listening to my talk. And I also want to acknowledge the support from the Moore Theory Centers, both at Harvard and MIT. So for both inviting me on a sabbatical leave and also providing some office space. So thank you very much. Let's get started. So conventional spin physics, this is where I built much of my career on. They're based on a number of celebrated interaction terms, such as the Heisenberg, Dzyalzinski-Moria, and Zeeman, all illustrated names in history of physics. And you might throw in some anisotropy term as well. And by combining all of these terms in a material-specific ways, you can explain a truly wide range of phenomena in magnetism, such as ferromagnet, antiferromagnet, spiral magnet, and even skyrmion excitations in some of these chiromagnets. And and one thing that's obvious from this general Hamiltonian is that all of these terms are at most spin bilinears, and we almost never get exact solutions, except perhaps in one dimension. And typically the higher order terms, such as the ring exchange, are considered less important and complicate the physics. So we don't normally talk about them very much. However, there was a dramatic change of perspective brought about by Kitev about 25 years ago, who wrote down a 4-spin Hamiltonian in complete disregard for the conventional spin Hamiltonians, and was able to show that the model is exactly solvable despite being a 4-spin interaction model. And not only was the model exactly solvable, but it was host to a whole number of very interesting properties involving topology, anyons, and quantum computation. So nowadays, Kitev model, the Toric code model, is something of a textbook material. And unlike the conventional spin models, the spins in the Toric code are defined on bonds. But of course, if you're someone familiar with the lattice gauge theory, this is rather natural. The Hamiltonian of the Toric code is a sum of projectors, and each projector acting on the ground state produces an identity. So in the specific case of the Toric code, these projectors are made up of these 4-spin product, like a product of Z and Z inverses, or a product of X and X inverses around the plaquette like this. And notice that I deliberately wrote the Z inverse here and the X inverse here. Normally, this is just X if you are just working in the Z2 space. But I will be working in the more general Zn subspace. And so these Z's and X's are the generalized Pauli operators. And therefore, the Z's and Z inverses are not the same. So technically, the analysis and so forth are a little more complicated, but there are some benefits to be gained from working in this more general setting. So I will adhere to the Zn Hilbert space throughout my entire talk. Okay, so Toric code is exactly solvable because every term in the Hamiltonian is commuting with every other term. And the same story applies to both the 3-dimensional Toric code, the X-cube model. They not only involve 4-spin exchange terms, but also 6 and even 12-spin exchange terms. And it was pointed out probably by a lot of people, but the place where I learned about this insight is these 2 papers by Hermele group and also Barkashli et al. These are the papers that appeared about 4 years ago. And what I learned was that all of these so-called exactly solvable stabilizer type models have the origin of their exact solvability coming from the so-called commutativity of the generators in the underlying lattice gauge theory. And once I understood what they were saying, then it became quite clear why all of these models were solvable. And I really grew fond of this view. And I decided to explore this view in my own fashion quite a bit. And so that's the story I want to share. So before going into that, let me give you a embarrassingly simple review of the U1 gauge theory. Of course, this is the most famous kind of gauge theory where the covariant derivative acting on the matter field consists of the gradient minus the I times the vector field. And the reason why this combination is a must can be seen from the following simple operation. So you define this a unitary operator using the matter density, psi dagger psi, as a generator. And then acting on some matter field like this will produce a simple phase factor, which is in principle position dependent. You can define another unitary operator out of the divergence of the electric field, and that acting on the vector potential produces the famous gradient of the gauge function. However, these 2 unitary operators are in fact not different. They are identical, provided that we impose these constraints relating the matter Hilbert space to the gauge field Hilbert space. And under these constraints, these 2 unitary operators become one and the same. And therefore, under the single unitary operation, this covariant derivatives simply gives rise to a phase factor. And therefore, one can construct a gauge invariant Lagrangian by simply taking the square of this covariant derivative. And that's how you arrive at this well-known gauge action, gauge invariant action for the matter field. Okay, and all of these mathematical manipulations based on this simple, well-known commutation relation between the A and E. And actually from this commutator, you can prove quite easily that the curl of A and the divergence of E, they always commute. And this is not only true in the continuum, but it's also true on some lattice, where you just replace this curls and the divergences by their lattice counterpart. So now, actually, this raises the question, this divergence of E was already used as a generator of some gauge transformation, but why don't we use this curl of A as a generator of some other gauge transformation? In fact, you can do that like this here. The only technical complication is that now, because this is a vector, you have to use a vector gauge function, which I call G. And similarly, you can introduce a whole vector set of charges, rho x, rho y, rho z, and also make a similar unitary matrix out of that. And again, by imposing the constraint relating the curl of the vector potential to the magnetic charge density, you can write down this sort of unitary transformations acting simultaneously on the matter fields, producing some phase factors, also on the electric field, producing this rather unusual form of the gauge transformation as the curl of the vector gauge function. So now the natural question is then, what is the appropriate covariant derivative? Well, in 2 dimensions, the answer is still extremely simple, because after all, there's only one orientation of the magnetic field. And likewise, there's only one kind of magnetic charge you can write down. So then the story is almost exactly the same as the case of the electric charge. So, so the covariant derivative is the familiar one. The only notable feature here is that this magnetic field operator now couples to the electric field rather than the vector potential A. So from the perspective of the magnetic charge, it's the electric field which acts like a gauge field. So to summarize, the E particles are covariantly coupled to the A gauge field, and the M particles are covariantly coupled to the E gauge field. And this is precisely the actions of the E and M quasiparticles in the 2-dimensional Toric code, as I'm sure most of you are already familiar with. Now, now the things get a little more complex in 3 dimensions, because now you really have to cope with the this presence of 3 magnetic charges, and gauge transformation rules for the electric field was more complex, as you saw just a minute ago. But after some searching, it's possible to write down a covariant form, which is this. Okay, so this psi's are the 3 possible magnetic charge operators, and these are various spatial derivatives, delta A, delta B. And the thing about this form is that although this is still first order in the derivative, it's second order in the matter fields. It has to be, otherwise you won't be able to satisfy this nice gauge covariance property. So the one immediate offshot of that is that the minimal action you can write down for these magnetic charges has to be fourth order in the matter fields. So being fourth order means that these magnetic charges are no longer free, because fourth order means they're already highly interacting. And what we will learn, and I will come back to this point in a little bit, in a little while, and the point is that this is precisely the actions that describe the dynamics of the M quasiparticles in the three-dimensional Toric code. Okay, so now let's get back to the so-called gauge theory interpretation of the two-dimensional Toric code.
Excuse me.
Yes.
Oh, when you mentioned M quasi-particle in 3D torical earlier, shouldn't the M should be a magnetic loop instead of just a particle?
Yes, yes. So yeah, that's the point I will come back to. And the interpretation would be that because these actions for the M particles are so highly interacting, and that's probably why these M particles cannot exist as a free particle, but they have to form magnetic loops.
Okay. We will hear more later.
Yes.
Thank you.
Uh-huh. Okay. So so in the lattice gauge theory, we had this A fields and the E fields. And what I'm going to do is this some so-called Hixing procedure, by which I mean that I will place this A and E operators in the exponents. Essentially, I will be exponentiating these gauge fields operators, and I will call them X and Z respectively. And then you can immediately show that algebraically, the action of a Z operator on some quantum state is the production of this phase factor. And the action of an X operator on some quantum state is to raise the quantum number by 1. So omega here is the nth root of the unity. So along the way, what you do is to reduce the Hilbert space from U1, which is the Hilbert space of the original lattice gauge field, to Zn. And this process is often called Hixing, and I will adopt the nomenclature likewise. So under the Hixing, then this divergence, this is actually a unitary operator. This is the unitary operator I wrote down earlier. So this divergence of E in the lattice form now turns into a product of Z's. And this curl of A in the lattice form turns into a product of X's and X inverses. But notice that these are precisely these operators which goes to form the various projectors in the two-dimensional Toric code. So now there's no mystery about the commutativity of the terms in the two-dimensional Toric code. They are just direct descendant of the commutativity of the divergence of E and the curl of A, otherwise known as the magnetic field, in the parent lattice gauge theory. And once you understood this connection, then the reason why these four spin interactions show up in the Toric code is quite trivial. Okay, the three-dimensional Toric code can be constructed in a completely similar manner. The only technical complications are that the divergence of E is now defined over 6 links rather than 4 links. So under the Hixing, it will become a product of 6 Z generalized Pauli operators. And for the curl of A, that's the plaquette operator. But now we're in 3 dimensions, so there are 3 orientations along which the flux can point. And that gives rise to 3 different plaquette operators. And that's why in the 3-dimensional toric code, you have this sum of 4 different projectors. And all of them commute by virtue of the commutativity of these divergence of E and the curl of A in the underlying lattice gauge theory. Okay, so the excitations in these models are defined operationally, operator-wise, as one of these unitary Higgs unitary operators acting on some state. Instead of producing a 1, it produces a phase vector omega. And when A acts on state, produces a phase omega, it's called the E particle. When this B operator acts on some state and produces a phase, it's called the M particle. Okay, and there are well-known mutual analytic statistics between these E and M particles. So now what I'm going to do is to construct some field theory descriptions capturing the dynamics of these quasi-particles. Okay, so in 2D toric code, there's nothing to speak of because all these results are well known. And furthermore, these are all very conventional forms of a U1 electrodynamics. And from this Lagrangian, it's possible to derive some conservation laws, which are also completely familiar forms. And there are a bunch of constraints that one has to satisfy. Namely, the divergence of E has to match the local E particle density, and the curl of A has to match the local magnetic particle density. And there are additional constraints coming from taking the time derivative of the density and invoking these conservation laws, which are these 2 equations shown on the right side. So altogether, there are these 4 constraints that one must implement at the level of a Lagrangian. And implementing this constraint is done by introducing a whole bunch of Lagrange multipliers. And in so doing, we arrive at such a Lagrangian, which is the well-known BF action. Okay, so this is sort of a physical derivation, if you will, of the BF action. And this action, as you probably know very well, describe all the mutual statistics of E and M particles in the 2-dimensional toric code. Okay, for the 3-dimensional toric code, the E particle is still free, so there's nothing to talk about there. The Lagrangian is the conventional one. But for the magnetic part, I already showed that the covariant derivative has to be of this form, involving 2 powers of the matter field and therefore 4 powers of the matter field in the action. And the continuity equation that follows from this action is also quite unusual. Okay, rather than being a divergence of something, it has to be the curl of some current operator. Okay, so this is ultimately a consequence of this rather unusual gauge transformation properties that we had to impose on both the electric field and also on this magnetic matter fields. Okay, so now this is going back to Jubin's question. It's well known that in 3-dimensional toric code, these magnetic excitations are not free. They always have to come in the form of these loops. And this is a nice picture that I've taken from a 9-year-old paper. And because of that, the correct description of the magnetic excitations in the 3-dimensional toric code is in fact in terms of vortex loops. And what I've done here is to sort of write down the particle-like action, which must be a description of the same vortex loop excitation. Okay, So I derived this form on the basis of these various gauge principles that I went through. But it's also my suspicion that ultimately this action must be able to have a connection to the vortex loop action, because we know that physically the excitations are in the form of vortex loops. So that connection is something that I have not quite made yet, but I highly suspect that there will be such a connection. Okay, so does that somehow alleviate your concern, Juven, or you have some other comment?
Maybe I need also to think of it. Maybe I'll follow up later. Yeah, thanks. Thank you.
Yeah, okay.
A quick question, but if you use the vortex loop, isn't everything linear there? Isn't it more natural there to just think of it as a 3-component vector and
3-component vector for the magnetic charge or for the vortex loop?
right, and then it'll just be some like some transformers in 2 form or something.
Yeah, so what I suspect is that eventually you start from this action and probably implement some sort of a duality transformation. And if you do it just in the right way, then you will probably find some sort of a 2-form gauge field action. Yeah, so I completely sympathize with your suspicion, but I haven't done the necessary algebra yet. Yeah, in fact, this is one of my one of the projects that I think maybe I should start focusing on during my sabbatical. Okay, so so as to the field theory, again, we write down all the constraints. Namely, the divergence of E has to be the electric charge density. The curl of A has to be the magnetic charge density. And there are also constraints relating the current densities of the electric particles and the magnetic particles to the time derivatives. And again, all of these constraints simply need to be embodied as Lagrange multipliers. And that process, that procedure actually is able to constrain you to this action, which after a little bit of massaging, you can prove to be exactly the 3+1 dimensional BF action. So in the literature, you will find that this 3+1 dimensional BF action is the correct low energy description of the excitation in the 3+1 dimensional toric code. But maybe because of the lack of my education, I was never really able to see a clear derivation behind such a statement. But following the sort of the steps that I have outlined here, it does lead you to the 3+1 dimensional BF action in a very natural manner. So I was quite satisfied. So one additional comment. So I wrote down this pretty horrible effective action for these magnetic, so-called magnetic particles, but then they look awfully complicated to analyze. So maybe an alternative is to discretize such an action. And so the way to discretize it is to pretend that I have these 3 species of M particles on a lattice, Mx, My, Mz. And again, by invoking the gauge invariance, gauge transformation properties of all these matter fields and all these electric fields, and requiring that ultimately the Hamiltonian can only consist of gauge invariant terms. The only kind of sort of hopping terms that I can write down are of this kind. which involves some sort of correlated hopping of mx in the y direction, simultaneously taking place with the hopping of the my particle in the x direction. So this is very much reminiscent of these quadruple models or fracton models that people are increasingly getting familiar with. And maybe it's interesting to notice that this three-dimensional Toric code model, which is not known to be the model hosting a fracton behavior, can still give rise to this sort of a correlated hopping physics. And maybe analyzing this sort of model in some ways might be interesting. Again, if you do this analysis properly, it might lead you back to the vortex loop picture that many people are already familiar with. Okay, so now let me jump on to the third model, which is the X-cube model, invented by our neighbors. So this X-cube model consists of some cube operator, which is a product of 12 spins on the edges of a cube, and some vertex operators consisting of a product of 4 spins. It's known to host a subextensive ground state degeneracy and some exotic excitations called the fractons and lineons. And again, what I learned from these papers by these papers is that X-cube model is also a descendant of what's called the rank 2 U1 lattice gauge theory. So what we normally call the U1 lattice gauge theory is in fact a rank 1. And the rank 2 means that instead of having a vector gauge field, we have a tensor gauge field. Okay. And this sort of idea was, of course, advanced very early on by CMSA before any of these things exactly solvable models. Well, it's well after Toric code, but I don't think CMSA was, what CMSA had in mind was Toric code. But anyway, and so it turns out that in order to sort of derive the X-cube model, you don't really have to write down the tensor gauge field in its full-fledged form, because the tensor gauge field you need is antisymmetric in the case of, it's symmetric and satisfies something called the hollowness condition. So after digesting all those details, it's possible to introduce just a vector field. That's enough to give rise to the X-cube model. So the bottom line is that you just define the this vector gauge fields and also the corresponding vector conjugate electric field. Now, what's changing is that the definition of the divergence of E is now quite different from the normal divergence of E that we know and love. So it consists of 12 different terms with various pluses and minuses. In the continuum limit, this is what it reduces to. So it's nothing like the divergence of E that we are accustomed to. And also the definition of the magnetic field is quite funny. It's like this. It's in the continuum form, it's like this. So there's, at least to me, there's nothing intuitive about these choices of expressions. The only thing that's for sure is that if you write down these terms in this particular combination, then the commutativity of all of these terms is guaranteed. Okay, so you can think of this funny D of E and funny B as the generators, new sort of generators in these rank 2 lattice gauge theory. So again, let's go ahead and play the same game. we're going to Higgs them by putting these generators into the exponents, and that will give rise to some spin operator, which consists of 12 different generalized probability operators, because D of E here consists of 12 different combinations of the E fields, and so on. Yeah. So this is how you get the X cube model. And of course, X cube model and its variations have been studied very, very extensively by many, many people over the last 10 years or so. And unfortunately, I'm not going to be able to do justice to most of them. But let me just focus on the gauge aspect of this X cube model, or the rank 2 U1 gauge theory. So again, the generator here is constructed in this way by making use of these two mutually commuting operators, D of E and some generalized magnetic field. And again, these sort of Gauss laws will relate the D of E to some local fracton density and relate the local magnetic field to some local lineon density. Okay. And you can work out all the gauge transformation properties of the A's and E's and fracton operators and the lineon operators. It's all technical, but you can do it. It's not terribly hard. And then again, you ask, what are the allowed forms of the covariant derivative? And this is the answer for the fracton part. And for those of you who have read and understood Pretko's, this very simple but very insightful paper, Fracton Gauge Principle, you will recognize this particular expression as one of the expressions he suggested as directly following from the general guiding principle of this fractonic gauge principle. Okay. Okay, so regarding the lineons, the proper covariant derivative for the lineons are like this. So the lineon Y operator, lineon Z operator have to show up in this mixed form and coupled to the X component of the electric field. And there are similar expressions for the other two components, which are obtained by permutations of the indices. And therefore, the Lagrangians for the fermion, for the fractons and the lineons are constructed in this manner. Okay, so what are the conservation laws? Well, for the fracton part, it's like this, has two derivatives. Now, the fact that you have these two derivatives showing up in the conservation law rather than a single derivative immediately suggests that a single charge cannot move, because there's an additional conservation law for the dipole moment. And so this is how, in some sort of hydrodynamic manner, you can immediately see this restricted behavior of the fractonic excitations. Regarding the lineons, the hydrodynamics is governed by expression like this, and plus similar expressions for the other two permutations of the indices. And although it's not that obvious just by looking at the equation, we've done some analysis in our preprint showing that the valid solutions of these lineon hydrodynamics is either a one-dimensional motion, or when it's trying to turn into other directions, it can only do so at the expense of creating other lineons. So an X lineon trying to move away from the X direction will end up creating a bunch of Y lineons and Z lineons. Okay, that's the lesson we get from us analyzing the hydrodynamics. And of course, that's what we also know from analysis of the lattice X-cube model. So it's quite gratifying that the hydrodynamic analysis results are falling in line with the analysis of the lattice model. Okay, you can go ahead and construct the field theory for the A and E fields, but it's exactly of the same form as the field theory written down by Slagle and Kim. So I will not have to repeat that. Okay, again, you can write down the lattice model for the fractons, and that's of this form. Now, this sort of hopping term is again very familiar. It was suggested in the context of a higher order topological insulator by Hughes and collaborators. I think they're still actively pursuing this idea, and it shows up in a different context, such as the X-cube model. But of course, the important difference from their perspective is that here we have to have this A gauge field now, because this is not a static one, this is a dynamic gauge field. So we have to incorporate them sort of at the 0th order level, which probably makes the problem a lot more challenging. And so these are the various hopping processes you can have for the fractons in the X-cube model. And also for the lineon hopping, you have this sort of a correlated hopping of the X and Y. So they're very, very similar to the hopping processes allowed in the three-dimensional Toric code. Perhaps not exactly the same, but very, very similar. Okay, so so far I have talked about 3 different models: 2D Toric code, 3D Toric code, and the X-cube, and they're all very well-known models. And what I have done is to sort of revisit these models from a perspective that's sort of consistent. And the consistent perspective is that of lattice gauge theory, and also by recurring the gauge invariance on the matter sector and the gauge sector, we were able to write down some effective Lagrangians for these various quasiparticles. And more often than not, these matter actions are quite non-trivial in the sense that they're not quadratic, and therefore naturally highly interacting. Okay, so I have 2 more models to show you, and depending on time and fatigue level, I will either cover just 1 more model or maybe cover both of them. Okay, so this is a model that my student Chinte and I wrote down about 1.5 years ago, maybe 2 years ago. And we were just playing around with some lattice model, wondering whether we can write down some stabilizer Hamiltonians of our own. And we kind of stumbled onto this model, which was exactly solvable. And the model was actually a sum of the 3-dimensional Toric code, which consists of these A stabilizers and C stabilizers, plus a term that we just stole from the X-cube model. Okay, so here this A term is exactly the one coming from exponentiating the divergence of E in the 3-dimensional Toric code. And these C's are nothing but the various plaquette operators of the 3D Toric code. And in addition, we also throw in this cubic term that played a prominent role in the writing down of the X-cube model. it turns out that you can have all of these terms in a single Hamiltonian, make them all commute, but the only caveat is that the Hilbert space dimension has to be 3. Otherwise, this new guy that we borrow from the rank 2 U1 gauge theory will not be commuting with the rest of the terms that we have from the rank 1 U1 lattice gauge theory. So that was the only caveat, but otherwise we had a perfectly fine commuting stabilizer Hamiltonian that we were able to solve and analyze. So now, because we had these 3 different types of terms, we have 3 different types of excitations called the freon, fracton, and fluxon. So freon is what's known as the E particle in the Toric code. Fluxon is the M particle in the Toric code, and fracton is the fracton. But we changed their name so that it sort of rhyme. So we call this the F3 model because there are 3 kinds of F excitations. So I won't go into the details of the properties of this lattice model, but so roughly speaking, the underlying backbone of our model was that we had 3 kinds of generators, 2 of which came from the rank 1 gauge theory, namely the divergence of A and the curl of A. Apologize for the interchange of the roles of A and E here for technical reason. And we also have this rank 2 generator. All 3 of them play a role now in our sort of hybrid theory. So as a result, our operators, unitary operators, are a bit more complex. In fact, this second form is the one we already had from the 3-dimensional Toric code. And what's new is that this unitary operator has both the U1 generator, rank 1 generator, and the rank 2 generator sitting in the same place. So that's the complication. But anyway, you can go through the same sort of gauge principle analysis, write down a various covariant derivatives, which are now quadratic in the derivatives, but quartic in the fields, and derive various conservation laws and so on. And it turns out that the gauge action for this F3 model was nothing but 3 plus 1-dimensional BF action of the 3-dimensional Toric code plus this additional term, which embodies the constraints of the rank 2 gauge theory. So after the dust settles, it turns out that the picture that emerges was not that much more complicated than what we already had for the 3-dimensional Toric code. So this exercise goes to show that in principle, it's possible to write down a additional sort of hybrid model for stabilizer Hamiltonians and even write down some field theory in some hybrid form. Okay, so here are a summary and various lessons that one can draw from analyzing these various stabilizer Hamiltonians from the gauge theory perspective. Okay, so now in the remaining time, I want to talk about the 5th model that we studied. But before going to that, perhaps I can take some questions you have any.
Yeah. Oh, sorry. Yeah, maybe just a little naive question, I guess. So
Yeah.
This looks to me very much like, oh, okay. So let me just ask this. Are you considering like a certain action of the rank 1 U1 on rank 2 U1? Like, do the sectors talk to each other, or? I don't think so, right? Because in each term in the action, for example, you don't have terms like A, just A times E, for example.
But yeah, but this electric fields operators dx and ey and z, they also enter in the definition of the 3 + 1 dimensional BF action. So we don't have a separate gauge field for the rank 1 theory and the rank 2 theory. It's more like exactly the same gauge fields, A and E, are showing up both in the rank 1 form and the rank 2 form.
Mm-hmm.
Yeah. So in that sense, I think you can say they do talk to each other.
But in a very like constrained way, I guess.
Yeah, I guess. Yeah.
Okay, I see.
Yeah.
Yeah, because I know, like, because from my understanding of like two gauge theories, there are, which is based on like group cross modules. I'm trying to sort of wrap my head around the construction that you're giving.
Yeah.
Okay, I'll think about that. Thank you.
Okay. We can talk about that in person, I'm sure.
Sure, thank you.
Yes.
A question like going back to your lattice model, you said that the slide where you had the lattice model. Yeah, you said the fracton is there, but it's actually confined. So is it actually so the only deconfined particle is like still the 3D Toric code? Is that what you mean?
Yes. Yes. So in the convention, in the X-cube model, I'm sure you're familiar with this drawing, where once you have a fracton, once you create a fracton quartet, you can expand them out at no extra cost in energy. However, in our model, because we have these extra plaquette terms, whenever you try to move the fractons apart, you end up creating all of these plaquette excitations, which we call fluxons. So we have these fractons, but they are threaded by a fluxon loop like this. And this fluxon loop will cost an energy in proportional to their length and create a tension. And as a result, the fractons are confined. They cannot move out to a large distance.
And so what's the ground state degeneracy of this model?
It's exactly the same as the three-dimensional Toric code. You know, it's n to the third power.
But then in what sense is this different from just a 3D Toric code? Because you don't have fractons as deconfined excitations anyway, right? Maybe a bit confused.
Yeah. So although we call them, by three different names, it turns out that fractons and fluxons are not really independent of each other, in the sense that trying to create a fracton, for example, will always end up creating a fluxon sort of cloud around it. And you can also see that from this field theory construction, namely when you try to write down a covariant derivative for the fracton field, it ends up being multiplied by these fluxon matter fields. So it turns out that it's impossible to write down a fracton covariant derivative on its own, nor write down a fluxon covariant derivative on its own. they always have to be combined in this fashion, and that's the only way to write down a covariant derivative. Okay, so that's another indication that in our particular model, these fractons and fluxons are not really, they're not really independent particles.
Mhm.
Yeah. So maybe this calling this F3 model is quite misleading, because after all, you don't really have independent fractons and fluxons in the theory.
Okay, thank you.
Yeah. Okay, so so we have been heavily invested in studying some three-dimensional models like you know, X-cube model, 3D Toric code, and some hybrid thing that we call the F3 model. But now I want to go back down to the 2 dimensions. And in 2 dimensions, I want to introduce some tensor gauge field. So instead of having a AX here and the AY here, I'm going to have an additional thing called the AXY. So this is a genuine tensor gauge field of a specific kind. So we have these 3-component gauge field per site with a missing I here. So now the question is, I'm given this rank 2 lattice gauge theory in 2 dimensions. So what's the corresponding lattice model? Okay, so that's the question we asked a while ago. And it turns out there are 3 kinds of generators you can write down. Here's 1, 2, and the third one. And I'm going to call that X electric charge and Y electric charge and magnetic charge. So you can think of this model with 2 electric charge excitations and 1 magnetic charge excitation, if you will. So now there will be 3 kinds of stabilizers obtained by Hixing the respective generators of the underlying rank 2 model. And therefore, your Hamiltonian will consist of 3 different terms like this. Now, the thing that we found quite interesting from analysis in this paper published earlier this year was that when you do this braiding calculation, right, you braid one of these quasi-particles called EX around the M, and the phase that we pick up is not just some, is not just some phase factor, constant phase factor. It's a phase factor that depends on the initial positions of the X particle, EX, and the M particle. And likewise, when you braid the EY quasi-particle around the M quasi-particle, you pick up a similar position dependence along the X coordinates like this. So a cartoon picture of what's happening is that in the 2-dimensional toric code, for example, when you braid an E around M or M around E, the resulting phase is just proportional to the number of particles that are inside the loop. And it's sort of a topological thing in the sense that deforming the loop continuously will not change the result. And that's typically what we expect of an ordinary anionic statistics. However, in our model, the result depends on where you started your braiding against where this test particle, if you will, is located. So of course, we made every possible check to make sure that this is the correct result. And at the level of the lattice analysis, we were absolutely certain that this is the right result. And so the question is whether there could be some field theoretic interpretation of these quite anomalous findings. And that's the field theoretic interpretation is what's reported in our recent preprint, posted, I think, on Monday this week, Monday or Tuesday. Okay, so let me just go through the main results. And in fact, I will talk more carefully about this in the upcoming condensed matter seminar in the department later this month. But anyway, here's a very brief summary. So this is a way we normally think about the anyon braiding. Namely, the braiding phase is proportional to the area integral of the charge density of the anyons that are enclosed in that loop, right? However, because of this relation, this is sometimes known as the flux attachment formula. And by virtue of this relation, you can convert this area integral to a line integral and make it really look like an Aharonov-Bohm effect. Okay, so this is a familiar scenario. In our case, the correct scenario looks like the following. The phase that we get from braiding one quasiparticle around the other is correctly captured by this kind of integral formula. So this is still an area integral, but it's not just the integral of the density, but it's the integral of the density multiplied by some coordinate difference. So the right way to think about it is to say that you're integrating the dipole density rather than the charge density. Luckily, it's still possible to convert this area integral to a line integral with some appropriately defined vector potential. And you can also calculate the curl of that vector potential and find that the result is not just the charge density, but charge density multiplied by these coordinates, which again makes the interpretation that what's shown on the right-hand side is something like the dipole density rather than the charge density. Okay, so there's an analogous formula for the braiding of the EY quasiparticle around the M, and so on. So yeah, and then the other question is, okay, so for this sort of anyonic braiding, we know what the right kind of field theory is.
That's just a question.
Yes.
Sorry for that. I just want to ask when you switch the slide, but anyway, just make sure the notation there and here and there in this and after the slide after you write this x of subindex y and y subindex. Maybe you explained that already, but can you recap again? The x.
Oh, this ax and ay?
No, the y subindex x and x subindex y.
Oh, okay.
On the right, yeah. Also, there is also, I think, probably typo, right? The e of x, is that the x of y, y of x, on the figure you show.
On the figure I show.
Yeah.
You mean this?
No, yeah, on the top. The e of x, you label this x sub y and y sub x should be x sub y instead of x sub x. But I don't follow that. Yeah, just there. Yes, x sub y.
Yeah. No, this is x sub x, y sub x. So this is x and y coordinates of the location of the E of x particle.
Mm-hmm. Oh, yeah. I see. Okay.
So, Jung Hoon, maybe just to clarify, I think what we may be confused about is that you have not just one, but two kinds of E particles, EX and EY.
Yes.
Could you explain why that is? Right, this is no longer a simple toric code or derivative of that.
No, it's not. So, yeah.
So you have dipole in x and y direction, right?
Yeah, it's a vector charge. I think that's what it is. That's why you need two types of X particle, right? Okay, so it's a vector charge, rank 2, U1. Okay.
Mhm.
Yeah, so I think Juven, when he writes down Y sub X, it means the Y coordinate of the X particle, and X sub Y is the X coordinate of the Y particle.
Yes.
Right.
Thanks. Thank you.
Yes, I understand there are so many X and Y's here, but yeah. It's all because I have two kinds of charges, X charge and the Y charge. Yeah. Maybe I should have said something like, you know, row A and row B. Maybe that would have been less complicating. Yeah. Okay. Okay. So actually, we're coming to the end. So we know very well that in the case of the conventional braiding statistics, the right field theory description that captures the braiding phases is just a well-known BF theory. So now we have this quite funny, you know, braiding results. So is it possible to go ahead and construct a sort of a dipolar version of the BF theory? And the answer is, fortunately, that we were able to construct such a theory. It's obviously much more complicated than the conventional BF action, but we were able to show in a pretty convincing way. And for details, I refer you to the preprint that we posted, that in fact, this is the right form. And by analyzing the various terms in the action, we were able to recover precisely this sort of braiding phases and so on. So so we do believe this is the right theory. Let's call it dipolar BF action. And you know, there's a similar okay. Probably you're all tired of seeing this sort of thing over and over again. So let me just be very, very terse. Again, there are some correlated hopping amplitudes hopping terms you can write down for the these X charges and Y charges, and also the magnetic charges. Yeah. So where does it come from? Okay. So here's a cartoon slide of what's happening. So when you normally braid like an E particle around M, you're just braiding an E particle, right? That's it. But it turns out that in our funny kind of lattice model, what happens is that whenever you try to braid an EX particle, for example, you cannot do that alone. It always has to be accompanied by the braiding of some dipole here, so that you have to move this particle and the dipole together. And the reason why that's necessary is that if you just move the EX particle alone, that of course breaks the dipole conservation. So by having this auxiliary dipole sort of tagging along, what this dipole does is to make sure that the overall dipole moment is conserved all during the braiding process. And because of the presence of the auxiliary dipole, then what you call the monopole density of the EX quasiparticle, for example, is not just the delta function, but it's the delta function accompanied by some auxiliary term coming from the auxiliary dipole. So due to the presence of this auxiliary term, you can go ahead and compute this quantity, and that gives precisely rise to these this sort of an emergent vector potentials whose curl was not equal to the density, but equal to the dipole density. So in the end, it seems to all fit together. Okay, so the kind of a broad lesson maybe that I want to emphasize is that this perhaps this dipolar braiding feature that we extracted from analyzing a particular model doesn't have to be confined to that model alone. Maybe this could be more general. Perhaps there can be other lattice models one can write down showing a similar dipolar braiding features. And if so, then this dipolar BF theory that we constructed could be more broadly applicable. And that's the kind of the hope that I'm entertaining at the moment. Yeah, okay, so I guess that's all I have to say. Thank you guys for your patience. Thank you.
Thank you, Jung Hoon.
Yeah.
Thank you, Professor Han. Question from the audience.
Can I ask a question? Thank you for the very nice talk. By the way, it's very, very interesting.
Thank you.
Yeah. So in this slide, you define a dipole BF action and still a 2D, right? 2D action.
Yeah.
And I see that you have tensor gauge fields.
Yeah.
So how do I interpret that? If I wish to consider a tensor, because A is kind of like a connection for the U1 symmetry that you have, right? If you say that you have a rank 2 U1 gauge symmetry, and you say that you have a rank 2 two-form connection, then yes, it's true that you have a tensor gauge field. But here, both E and A are both tensor gauge fields. So I think, I don't know if this is right, but I think that the gauge theoretic interpretation is that they're both two-form gauge fields, right? One is dual to the other.
I think so, yes.
But like that's a four form, right? When you put them together, you get a four form.
Does it have to be? Because, you know, this A tensor gauge field and the E tensor gauge field, they're actually conjugates to each other. So, so maybe.
Because in what we usually call BF action, it's just, you know, you have B and then F, and then you put them together. Like if B is a two-form gauge field and A is one form, then you get a four form, and you integrate like a 3+1, and you get like a 3+1D gauge theory. But
I see. So maybe in a very layman term, what you're saying is that because here EXX has two indices and here AXX also has two indices, so overall this thing has four indices. So that's kind of what you are thinking about, right? When you say it's a four-form gauge field.
Or like maybe you can also imagine like maybe putting B star F, right? The Hodge star, B star F, then that would be no problem. But that's I don't know if that's a BF action, you know.
I'm very naive when it comes to this sort of differential geometric interpretation of the gauge field. So you might have to enlighten me a lot on this more mathematical way of looking at these actions.
Okay.
All I can say for sure is that this action is correct when it comes to capturing these dipolar braiding statistics.
For sure.
Maybe it deserves to be further sort of studied and generalized.
Because I've also seen something very much similar to this when there are people that study like subsystem symmetries and like quantum lattice systems with subsystem symmetry.
I see.
And that particular, like let's say you're in 2D and then you have a subsystem symmetry along one direction, and then the dipole charge along that direction is conserved. And they write down something very similar to this. But it's a Yang-Mills theory, which is like so they define a two form, which is quote unquote magnetic field, a two form magnetic field, which is a tensor field, minus the U1 curvature that you usually get. Yeah. So and then it's this quantity with a hot star in front of it. This quantity contracted with itself, essentially. Yeah. And that tells you that on shell you have dipole conservation, which is right. If you source the B form and you source the A form, and then you look at the conservation laws, then you find like mobility restriction and stuff like that, which is I can send you the paper.
Yeah, please. I don't think our lattice model has a subsystem symmetry, but still it would be very nice to look into that paper and see if it has connection to what we have here.
Okay. Yeah. Sounds good. Thank you.
Yeah, thank you.
Maybe I have a question about the Hamiltonian formulation earlier. That probably some model you call F3 or something. F3 model?
Oh, F3 model. Let's go back there. Yes.
I just want to make sure, can you remind me, like, is this Hamiltonian a deformation or combination of the 3D Toric and also 3D SQ model in some way? Which means that can you start from either of 3D Toric, 3D SQ model that you do some Hamiltonian deformation?
Yeah.
Is that part of deformation of either of the model, or is that a totally modification, not the deformation? Deformation in the sense by turning on some coupling.
Yeah.
Coupling can tune up to the model you have. That's the question. If it's clear.
Yeah, I guess you can call it a deformation in the sense that, okay, if you have just the sum of these A and C stabilizers, then that's a 3D toric code. And you throw in this B stabilizer term. Instead of saying plus B, let's say it's a plus lambda times B, and you gradually increase lambda from 0 to 1. And yeah, so yeah, in that sense, I think you can call this F3 model a deformation of the 3D toric code.
So it's a deformation of 3D toric code, but not a deformation of a 3D SQ model, or is it also a deformation?
No, it's not a deformation of the X cube model. It's a deformation of the 3D toric code.
Great.
Yeah. Yeah.
Actually, is the B terms some product of C's or something like that? Or because you're saying the degeneracy doesn't change, so.
Yeah, in fact, that's the case. Yes. Jinte, are you there?
Yes, I'm here.
Yeah. So yeah, can you remind me the BC is a product of the CPs, right?
Yeah, that's true.
Yeah. It's something that actually we noticed and mentioned in our paper.
But then the B is not really adding anything, I guess. Maybe that's why I'm confused. Well, I guess you're saying it's just 3D toric. But,
yeah.
I guess as a low energy, it's not adding anything.
Right. Yeah. I agree with that assessment. Yeah, but we came to that realization well after we wrote this down and analyzed it. In fact, what we also did in this paper is that we also considered a model where you only have the let's see, you only have the A term and the B term, and that changes. So you don't have the fluxon term. And that changes the ground state properties. It changes everything completely. Yeah. So in fact, that was the bulk of the analysis done in our paper. but that's something I'm not talking about today.
Uh-huh.
Okay. If no further question or comments, we should thank Professor Han. 감사합니다. 매우 감사합니다. Thank you very much.
감사합니다.
Nice talk. Thank you.
Thank you.